In this chapter, we will be studying the derivative rules. In this lesson, we will be looking at the chain rule.
All right, hi everybody. So we're going to be talking about the chain rule today. Now, the chain rule is used when you're going to find the derivative of composite functions. And you will be surprised at how often this actually comes up. And in fact, once you get this rule down pat, once you understand exactly what's going on with this completely blows open everything. You'll be able to take the derivative of so much more than you have up to this point. This is an extremely powerful rule, the chain rule. Now, what happens here is if the derivative, of g of x exists and the derivative of f evaluated at g of x exist, if they both exist, then we're going to define some capital F. And now capital F is going to be the composition of those two functions, just like this. Okay. Now I'm just going to give you the rule here. So the derivative of capital F is going to be equal to the derivative of little f at g multiplied by the derivative of g. Okay. Now, this is typically the way you're going to think of the chain rule as we go through and apply it here. Another way of looking at it that is useful in certain contexts here, and actually in this particular case, this little bit of notation here, this is about as far as we're going to get by way of proof, if I can even use that word here. So what we're going to do here is we're going to write y equals fu. Okay, and yes, I just said fu. Laugh about it. Haha, that's not. Anyway, grow up. F of u, where u is equal to g of x, and this implies, if you go back to that y is equal to f composed with g. Okay, that's exactly what we're saying here. Then what we can do here is when you take the derivative of y, so dy by dx, that's going to equal dy by du. Okay, so let's just take a look at this. Dy by du. If we go back up to the y function that I've got written here, remember we're using the letter u as the independent variable there. So f is a function of u. There's no x there. Okay, so we're going to take the derivative of y as if u was the independent variable. And then what we're going to do is we're going to multiply that by the derivative of u. Okay, and u is a function of x. And in this case here, x is the independent variable. So we're going to multiply by du by dx. Now, what happens here, really conceptually, is that the du differential cancels here, and we're left with dy over dx, exactly what we're looking for. Now, the way that kind of plays itself out in the question can be a little bit awkward. I don't deny that. Okay, and we'll probably take a look at a question here where we'll do it like that. In fact, I might use that as kind of a lead-in to the more complicated problems. But that's about as far as I'm going to get by way of proving that this works here. So dy by du multiplied by du by dx, okay? And so that u function is the one that's being composed there. Now, I am not going to go through a proper proof of this because it really is more advanced than we need for this particular course. I did try a proof once in my class, and I was so pleased with myself. I was very proud of the proof that I had thrown up on the board. But when I turned around and saw the looks in their eyes, I realized that had been a complete waste of time. It was well over their heads. It's not necessary for what we're trying to accomplish anyway. We just want you to be able to apply the rule. Okay. So anyway, let's take a look at just a handful of problems here, and I'm hoping that by the time we get through 4 or 5 of them here, that the pattern will make a lot of sense. Okay, so let's find the derivative of y equals 2 minus x cubed to the 50. Okay, to start this one off here, I am going to use that y and u notation here. So let's just take a look at this. Remember when we were discussing that little bit of notation there, y was a function of u. So y was f evaluated at u. So now compare that, compare that to the question that we've got here. What would make sense as a u function? Well, I hope that when you see this as being composed here, that it makes sense that u would be equal to 2 minus x cubed. And so what we've got here then, this function here would be y is equal to u to the 50. And then over here, we've got u is equal to 2 minus x cubed. And so then when I compose y with u, I'm just taking that 2 minus x cubed and putting it inside the u to the 50. Now, according to the chain rule, to take the derivative of this, what I do, okay, dy by dx is going to equal dy by du. Whoops. Let me just clean that little bit up there. Dy by du multiplied by du by dx. Okay, so what does that look like? Well, dy by du, if I take the derivative of y with respect to u here, that's this expression right there, I will bring down the 50. Okay, I'm just going to apply the power rule, and I will subtract 1 from the exponent. So 50u to the 49 multiplied by, and now I'm going to take the derivative of this expression right here, but this time with respect to x. Okay, and so now the derivative of 2 is just going to be 0. The derivative of x, I want that to be black here. The derivative of negative x cubed will be 3x squared. Okay, good. So now when we multiply those together, and I'll come up here, we'll get that dy by dx is going to equal 150, u to the 49 multiplied by x squared. Now, I'm not particularly fond of the way this answer looks, though, because I've got this u in there. And in the original expression, I didn't have that u. So now what I'm going to do is I'm going to go back and replace u with 2 minus x cubed. So this becomes 150 multiplied by 2 minus x cubed all to the 49, and then multiplied by x squared, which, quite honestly, I would probably write more like 150x squared, 2 minus x cubed to the 49. That looks better to me. But I'll be honest with you, if I put a little red line here, now this might not necessarily be true of all your teachers here, but I like it better when you take the negative out of there if you can. Now notice that that's to an odd power. So I should be able to factor a negative out of that. Okay, so basically I'm making this 150x squared. What I'm going to do is I'm going to factor a negative out of that binomial inside there, which will turn this into x cubed minus 2. Okay, I haven't taken the negative right out yet, so it's still all to the 49. But that negative 1 right there to the power of 49 stays negative 1. So I can pull that right out, get negative 150 x squared, x cubed minus 2 to the 49. Okay, now, really, is that much different than what I wrote up here? Well, no, but isn't that pretty? Oh, doesn't that look better? Okay, now, if it doesn't look better to you, if you're sitting there going, no, it doesn't look any different to me, okay, bear in mind that there's going to be a lot of people out there that actually look at that and say, yep, that looks way better. That's the way I would write that. Now, by the way, before we go on to the next problem here, I should really point out here, and I should have pointed this out right at the beginning here, notice how this is a huge improvement over what you would have had to have done prior to knowing the chain rule. Prior to knowing the chain rule, we would have had to have come back up to here, okay, and taken this expression and expanded it out to the 50th. Now, even if you know binomial expansion, expanding that binomial out to the 50th power, that's going to take a while. Okay, that's going to take some effort on your part, and then you would take the derivative of each of those terms individually. Okay, now, and that's going to be really, really big. And the answer that you get would end up being the expansion of this expression down here. But isn't this a lot more compact? Isn't that just nicer there? The chain rule really is a huge step forward. Okay, it does make this material a lot easier to work with. Anyway, I should have commented on that immediately. But let's take a look now at another example. All right, now let's find the derivative of y equals 1 minus 2x cubed. Now, in this particular case here, maybe what I'll do is I will show you how the expansion and the chain rule kind of link together. Okay, so that first one that we did there and I know I kind of did that and I botched that. I did that in the wrong order. I really should have discussed how hard it was going to be to expand that before I talked about the derivative. Here, this one is actually relatively easy to expand. Now, let's maybe expand that first. So y is going to equal, this will be 1 minus, okay, 3 multiplied by 2x, okay, plus 3 multiplied by 4x squared minus 8x cubed. Now, I'm doing that fairly quickly here, merely because I'm applying the binomial expansion, okay? So I'm using combinations and I'm using the decreasing powers of the first term and increasing powers of the second term to do that a little bit quicker there. So if you have forgotten that, that would be something that you might want to review. Whoops, there we go. Okay, so now when I take the derivative, y primed, well, the derivative of 1 is going to be 0. The derivative of negative 6x is negative 6. The derivative of 12x squared will be 24x. And the derivative of negative 8x cubed is going to be negative 24x. Whoops, shoot, not x cubed. It'll be x squared. So it's a little too quick with that. Now, when I take a quick look at that, I see a common negative 6 that I'm going to factor out. And I'm going to change the order of everything here. That's going to give me a 4x squared plus 4x minus 1. And that looks to me to be equal to negative 6. Looks to me like when I factor that, I'm going to get 2x minus 1 squared. Okay, so there's my derivative. Now, and I did that sort of the long way. Or what I could do here is, again, I could use the chain rule here. And once again, I'm going to use the u and the y notation here. So I'm going to say that y is some function of u. Now, whoops, it's not coming through there. Now, when I take a look at the original function, you got to think here, okay, well, if that's true, what would u be? And I hope it's pretty clear that if u is the interior function, it's going to be 1 minus 2x. And so that means y as a function of u is u cubed. So now, if I want to get dy by dx, that is going to be dy by du, okay, multiplied by whoops. No, I pulled out the wrong variable again. I'm so excited about where this is going. Du by dx. So looking up, y is equal to u cubed. So dy by du will be 3u squared. That is just the power rule. We'll put those in parentheses this time. When I use the cross for multiplication, it's getting a little confusing here. And now when I multiply by du by dx, okay, looking up at what u is, that's just going to be negative 2. Okay, now multiplying that together, I'm going to get negative 6u squared. Now, u is equal to 1 minus x squared, so that's going to be negative 6, 1 minus 2x squared. And again, when I look at that, I'm not particularly fond of the way that looks. I don't like having the 2x at the end, so I'm going to factor a negative out of that. And that's going to leave me with 2x minus 1 squared. Whoops, sorry, that negative should be a little bit bigger there. Now, when I square that negative 1 out front to get it outside of that parentheses there, negative 1 squared is going to become positive 1 multiplied by the negative 6 that's already out there. Well, it's just going to stay negative 6. And that's going to be 2x minus 1 squared, which is exactly what we got over here. Okay. Now, when you compare the two bits of work that I did here, okay, it really, in terms of the number of steps it took, it's really not that much of a savings to use the chain rule. However, that's because the exponent up here was 3. If the exponent was something bigger, then this does become a significant savings, like it did in that previous question where we were really kind of blowing that open. I wanted you to see to the 50, how quickly that you could take the derivative of that. But here, you could go either way, but you do end up getting the same result. I really encourage you, though, to use the chain rule when you can. Let's take a look at some more examples. All right, now we're going to find the derivative of y equals the square root of 6x minus 8x squared. Okay, now I might be tempted to write this, and actually it's not even that I'm tempted. I really need to write it this way, as 6x minus 8x squared all to the 1/2. Okay, I really can't take the square root with that. The derivative with that radical notation in there. I really got to convert it to an exponent here. Now, I can't do with this question what I did with the previous question. I don't really have a tool for doing a binomial expansion when the exponent is a fraction. So I really do need to use the chain rule in a case like this. Okay, please, I beg of you, don't try to distribute that 1/2 to both of the terms in the binomial. You are not allowed to do that. Okay, that is not a rule. And if you're sitting there thinking back, saying, "Yeah, I kind of think it is a rule," I remember being taught that. No, you weren't. You're misremembering that. Okay, there's no rule that distributes that exponent like that across a sum or a difference. So now, in this case right here, we are going to recognize, again, we're going to think of this as that where y is a function of u, and in this case, the u being inside the function that's being composed there is going to be 6x minus 8x squared. Okay. The pen is being a little slow here to register. But anyway, so my derivative dy by dx is going to be dy by du multiplied by du by dx. Okay, so in this case, and I didn't write this out specifically, but this means that my y function here, I'll write it down here, my y would be u to the 1/2. Just wait for that to pop up. So when I take the derivative of y with respect to u, that's simply going to be 1/2 u to the negative 1/2. Bring down the exponent, subtract 1 from the exponent. That's just the power rule. Put those in parentheses. And now the derivative of u with respect to x, well, just take a look here. The derivative of 6x is just 6. And the derivative of negative 8x squared is going to be 16x. Okay, now I'm pretty pleased with how that looks. I'm going to simplify it a little bit. First of all, I know that u with the negative exponent is going to go down in the denominator. So this will be u to the 1/2 down in the denominator. And then I've got this coefficient of 1/2 out front. I'm going to distribute the 1/2 through that second binomial. So half of 6 is 3, half of 16 is 8x. There it is. So I've got 3 minus 8x over the square root of u. So now all I really need to do, okay, to finish my derivative is to get rid of the u variable inside there. Okay, whoops. Again, I don't know why this is hesitating as much as it is. So my numerator will be 3 minus 8x over the square root. And u in this case, we saw over there was 6. Whoops. Yeah, see, as soon as I did that, I know it's going to overlap there, and I don't want it to, so I'm going to just erase that. Okay, try that again. This will be 6x minus 8x squared, and then we're going to square root that. Okay. Okay, now, that's fine. That's a good answer. I would be tempted to move things around a little bit, particularly in the numerator. I'm going to factor out a negative and make that positive 8x minus 3. Again, because I like having that, the highest degree term first. Now, I would be tempted to do the same thing in the denominator, and I will, but I'm not going to be able to do much with it, okay? Mostly because when I try to take a negative out of that, I'm not going to be able to move the negative out of the radical. So really all I'm going to be able to do is just change the order here. Now, I could factor out in that underneath that radical there, I could take out, for example, a negative 2x to factor that. but that's really not going to get me anywhere. I would still have to write it in there. It's not like anything's going to cancel. So that really is about as simple as I can make it. But it does look better having the quadratic term first in that expression, just like up in the numerator. It does look better to have the linear term first. Anyway, I like the way that looks better than I like the way it looks that one step up. You're going to have to figure out, though, with your teacher what your teacher wants to see in an expression like that. Okay, now let's find the derivative of y equals 5 over 2 plus the square root of 3x squared minus 4. Now this is an interesting one because this is going to take this one step further. Just to make this a little bit clearer so that you totally see why I say it like that, I'm going to rewrite this by bringing up the exponent. So I'm going to make this 5 multiplied by, in parentheses, 2 plus 3x squared minus 4. This is underneath the square root. Oh, where's that square root? There it is. All to the negative 1. Okay. Now, I'm going to take this and rewrite that as 5, 2 plus, I'm going to put this in brackets, 3x squared minus 4 to the 1/2. And that's all to the negative 1. Whoops. Sorry, that I don't know why that did that. That should look like that. Oh, that looks terrible. Okay, now I can't deal with that. I got to erase this just a little bit right here. Make that look better. Oh, I keep hitting it, but nothing's going away. There we go. So 3x squared minus 4. Okay, now, when you take a look at this, you see two sets of parentheses, which means we've got two nested functions. Or in other words, we've got a function composed with a function composed with another function. So what I'm going to do here, this is now going to be the same as y equals f of u of v of x. Okay? So isn't that kind of neat there? So, oops, there should be one more. There it is. I was going to say there should be one more parenthesis there. So how do you handle that? Well, what you do is you simply multiply the derivative of the outside of this, of the u of v of x, multiplied by the derivative of u at v of x, multiplied by the derivative of v of x. So now let's identify what our different functions are here, okay? Y as a function of u is really going to be 5 multiplied by u to the negative 1. Okay, and there we go. U, in this case, is going to be, now remember, u is now a function of v, and if I take a look inside there, that is going to be 2 plus v to the 1/2. Okay, just waiting for that to come up. There we go. And then finally, v, which is the innermost function, okay, is going to be 3x squared minus 4. And there we go. So now, to find the derivative of y with respect to x, that is going to equal dy by du multiplied by du by dv. Just waiting for that to happen. Multiplied by dv by dx. And then you see how these differentials here, okay, are going to these differentials here are going to cancel the du and the du, the dv, the dv, and you'll be left with dy over dx. Okay, so now let's figure out what these pieces are here. So dy by du, okay, is going to equal, now remember, y was 5u to the negative 1, so it's going to be negative 5u to the negative 2. Okay. Du by dv, okay, du by dv is going to equal, well, now that was 2 plus v to the 1/2. Well, the derivative of 2 is just 0. The derivative of v to the 1/2 will be 1/2 v to the negative 1/2. Okay, when that pops up, there we go. Oops. And then dv by dx is going to equal 6x. Just waiting for that to pop up. Okay, good. Now, I'm going to put that all together, except I'm going to have to erase a little bit here, so just that I have some room for it. Putting that all together, dy by dx is going to equal negative 5u to the negative 2. Come on. Multiplied by 1/2 v to the negative 1/2 multiplied by 6x. And there it is. Okay, so now we're just going to substitute back in the original expressions here. Now, by the way, I'm going to simplify this. I should probably simplify this just a little bit before we do this. 1/2 of 6 is going to be 3. There's also a negative 5 in the numerator. So it's going to be negative 15x over, and I've got a u squared v to the 1/2 down in the denominator. Whoops. Oh, sorry, that's getting a little messy there. Let me just at least get rid of one of those lines there. There we go. Okay, almost there. So now this is going to be negative 15x over, well, v, okay, to the 1/2 here. V is going to be, I had said it was 3x squared minus 4. So it's going to be the square root of 3x squared minus 4. U, on the other hand, u was 2 plus v to the 1/2. So I'm going to put down here, remember this is going to be u squared. So this is going to be 2 plus, and I already know that v was 3x squared minus 4 to the 1/2. Now just waiting for the, oh, that's not nearly as nice as I'd like that to look, but anyway, that is a 4 right there. Okay, so there you go. Negative 15x over 2 plus, and in brackets 3x squared minus 4 to the 1/2, and that's all squared, multiplied by the square root of 3x squared minus 4 in the denominator. So when you're doing the chain rule where you've got nested functions, really all you're doing is you're taking the derivative of the outside function, then multiply by the derivative of the inside function, and then multiply by the derivative of the inner function, and you just keep going in here. But please bear in mind that, like, when I took the derivative of, in this particular case here, and I'm going to switch to the red here. When I took the derivative of u, or sorry, I should say y of u, remember that the u function stays in there. Like, I didn't put the derivative of u in here. That is u. This is the derivative of y was going to be negative 5 over u squared. Well, there is my u. Okay. I'm just trying to get you, like, please remember you're still working with composed functions. Don't just take the derivative of everything and multiply that together. That would be incorrect. It's the derivative of the outer function with its inside function multiplied by the derivative of that inner function. We're going to take a look at one more example here, and I hope that little bit there gets clarified if it's not clear to you right now at this point. Okay, now we're going to find the derivative of y equals, and in brackets, x squared plus 1 over x plus 1, and that's all to the 10. So we're going to do this example here. I'm going to try to do it without referring to the u and the v sort of functions here. We're going to just kind of take it the way it is and work our way inside the composed functions here. But in addition, the importance of this question here is that it's going to force us to use more than just the chain rule. Okay, so when we take a look at this one here, and I'm going to do this one two different ways here, but when we take the derivative of this one, I notice that I've got this function to the 10. Okay, so here's what I was trying to get at before. I'm going to take the derivative of whatever's inside here to the 10. And so actually what I'm going to do here is I'm going to kind of cover this all up. It's going to be this right here to the 10. So red splotch to the 10. And so the derivative of that, I just want to change pens here, is going to be 10 multiplied by that all to the 9. Okay, now that should be coming up here in just a second. Good. Now, what I put inside this parentheses here is not the derivative of the inside. That's what I was trying to get at before, to communicate at the end of that last example here. It's not the derivative of what's inside. It's actually that function that's inside there right now. So that becomes x squared plus 1 over x plus 1. That's the interior function. Now we're going to multiply by its derivative. Okay, so we took the derivative of the piece outside the parentheses without changing what's inside. Now we're going to multiply by the derivative of what's inside. And in this particular case here, this is going to require the quotient rule. So the derivative of the numerator will be 2x multiplied by the denominator. Just waiting for that to register. Okay. Minus the numerator, x squared plus 1, multiplied by the derivative of the denominator, which in this case is just 1. And that's going to be all over the denominator squared. And again, just waiting for the pen to register that. Good. Good. So now, when I take, to simplify this, I'm going to factor out the expression that I have where I took the derivative using the quotient rule. So I can see, actually I can't see much. In fact, I don't know why I was saying factor out here. I'm actually going to have to expand that out. That's the exact opposite. So I'm going to have to make that 2x squared plus 2x minus x squared minus 1 all over x plus 1 squared. Okay, so that is going to get us 10 x squared plus 1 over x plus 1 all to the 9. And over here, well, 2x squared minus x squared is just x squared plus 2x minus 1 over x plus 1. Whoops. No, I'm going to have to fix that as soon as it comes through. Oh, no, that's okay. X plus 1 squared. Okay. Now, I don't think I can factor that numerator any more than that. At least it's not looking like it. However, when I make these videos, sometimes I do goofy things. But in either case here, but look what I can do with the denominator. So I've got this 10, and I'm going to write this as x squared plus 1 to the 9. Now, as soon as the pen comes through, you're going to see what I did there. I'm separating the numerator and the denominator there. Here, I'm going to get x squared plus 2x minus 1. Wow. Okay. Now, in those two factors that I've got there, I've got an x plus 1 to the 9 and an x plus 1 squared. So putting those together, this is going to get me x plus 1 to the 11. And this is one way of doing the derivative. Okay. And so this is an example of the chain rule together with the quotient rule. Or we could do this differently. And some of you are actually going to really appreciate this, because if you don't particularly like the quotient rule, there is another way around that. What you can do is take that original expression and make that x squared plus 1 to the 10 multiplied by x plus 1 to the negative 10. Okay, now I'm just waiting for that to, oh, okay, wow, that didn't come through at all there. Let me fix this. Okay, let's fix this up here. That didn't look right at all. Whoops. Just want you all to know that the technology was supposed to make this easier. And yet this is becoming very awkward here. Okay. So now when we take the derivative of this expression here, we're going to use the product rule, because I've got two factors multiplied together. Okay, at least that's the first rule that jumps out at me when I take a look at this. So y primed is going to equal, now when I try to take the derivative using the product rule though, I have to now take a look at that first factor. And to take the derivative of that first factor is going to require the chain rule. So I bring down the 10 multiplied by x squared plus 1 to the 9. That is the derivative of the outside of that factor. Now I move in and I take the derivative of the x squared plus 1. Now, if you want to think of it like we did previously, this is now the u part. I'm taking the derivative of the u, and in this case, that's going to be 2x. And I will multiply that by the second factor there, which in this case is going to be x plus 1 to the negative 10. And hopefully that comes up in a second. Good. Now I'm going to add to that, okay, because this is how the product rule works. I'm going to add to that the first term. That should come up in just a moment, multiplied by the derivative of the second term. Now, again, I look at my second term and I get x plus 1 to the negative 10. That's going to require the chain rule to take the derivative of it. So I'm going to bring down the negative 10. This will be x plus 1. Just waiting for that to show up so I know where to put the exponent. I bring down the negative 10. Now, be careful about this because when you take 1 away from negative 10, you're actually going to get negative 11 up there. I needed the exponent to get 1 smaller. You should see that in just a second. Okay, good. Now, let's factor. Between those two expressions, I can see I have got a common 10. Now, I did put an equal sign there. I'm just waiting for it to show up. 10. I'm going to take out an x squared plus a 1. The smallest exponent on that will be 9. Whenever that chooses to write. X plus 1. And now in this case here, x plus 1, the smallest exponent is actually going to be the negative 11. So as soon as I see that factor pop up there, I will put the negative 11 on it. Just anytime. Whatever you feel like. There it is. So negative 11. Now, this is all going to get multiplied by, well, what am I left with? Okay, out of that first term there, now bear in mind this is going to be multiplied by. Out of that first term, I took out the 10, the x squared plus 1 to the 9, so that is going to leave me with 2x. And then I took out the x plus 1 to the negative 11, so that's actually going to leave me with x plus 1 to the 1. Okay, now in that second set of terms, or sorry, set of factors there, I took out the x squared plus 1 to the 9. That's actually going to leave me with x squared plus 1. But I have a negative there. I took out the 10, but I still have that negative there. So this is going to be negative x squared plus 1. I'm just going to wait for that to show up so I know where to put the square brackets at the end here. Man, I apologize. It's not supposed to be taking that long. Okay. So now I have got, when I put this together finally, okay, this is going to be 10 x squared plus 1 to the 9. This part is going to be over. I'm going to just simplify this as I go here. This is going to be over. Whoops. Okay, don't know why it's doing that. X plus 1 to the 11. And then inside the square brackets, okay, inside the square brackets up here, I'm going to get 2x multiplied by x minus x squared. That is going to give me x squared. 2x plus 1 is going to give me plus 2x. And then the negative, when it distributes through, will just get me a minus 1. And you should see, or you should be seeing, that that is actually exactly the same derivative as we got before. Okay, these two are exactly the same. So it shouldn't matter, okay, whether you choose to look at this as a chain rule with an inside quotient rule, okay, or bring that apart, bring that exponent down and make that actually a product rule with two different chain rule factors. Should end up in exactly the same spot here.